Very good morning to one and all again. Today, like Professor Naoki Shanwara will be delivering the second lecture of this 4th day ongoing 5-day GAN course. The topic of this second lecture of today's is Theory and Technology of Rectenna, specifically rectifying antenna for energy harvesting. Without any further delay, I invite Professor Naoki Shanwara for starting the talk.
Hi, hello again, welcome back. So next, I'd like to introduce the same Rectenna technology, but I focus on the energy harvester, low power rectifier. As I mentioned, if we can develop very excellent rectifier close to, for example, 95% or 100%, if we input power is very weak, like an energy harvester, efficiency suddenly decreases. By the junction effect of the diode. So, but as I answered in the previous talk, unfortunately we cannot control the power density at the energy harvesting. Power source is the other one, TV tower, Wi-Fi source, or the other, so we cannot control the input power in the energy harvester. So, how do we design the good efficiency rectifier even at low power, below junction voltage? So now I'd like to introduce a very interesting approach to increase the efficiency. So as I mentioned again and again, in this talk, I mainly focus on the energy harvesting. Of course, additionally, it involves the ubiquitous wireless power transfer. And this is a typical ambient radio wave around there. TV, radio, and amateur wireless communication, Wi-Fi, mobile radar, GPS. Do you have any ETC or ETC other in India? I don't know. But they use microwaves mainly. So ETC, in Japan we use a 5.2 gigahertz, and the GPS we use a 2 gigahertz, etc. And some group measure the power density of ambient wave around us. For example, this is a Japanese case. So close to my home, my friend measure the power density around us. And mobile multimedia, digital TV, cellular ABS, etc. And frequency is here. And in this case, power density flux around us approximately 100 microwatt below. But it's a typical power density, I think so. So from this power density, we can harvest the ambient radio wave. This microwatt per square meter, not square centimeter. Square meter, we have only 100 microwatt. It's too tiny. So rectifier technology is most important to increase the receiving power, because we cannot expand the area of the antenna for mobility, for convenience. So rectifier technology is very important. So this is one example of the energy harvester in Japan. And in this case, they propose the multi-frequency energy harvester, because power density for one application is decided. So to increase the input power, they propose 3 radio waves will be gathered into one rectifier, for example. And in this case, under the 100 microwatt per square meters area, they derive this thermal sensor only by the harvesting wave, for example. And I'd like to introduce some interesting R&D result in the world. For example, this is an energy harvester developed by the University of Tokyo Group and Georgia Institute of Technology. And they harvest the TV broadcasting wave. This is a Japanese TV tower, so Tokyo Tower if you have a chance to visit Tokyo, this Tokyo Tower is one of the very famous sightseeing place. And from this Tokyo Tower, they gather this ambient TV broadcasting wave, and they drive some sensors here. And the same group, University of Tokyo group, developed very interesting energy harvester. Energy harvesting from the outside of the microwave oven. Of course, I introduced yesterday or day two, what I forgot it. But inside the microwave oven, there is much power, close to 1 kilowatt microwave power inside. So there is a pattern to harvest the inside microwave of the microwave oven. But we don't have a good semiconductor now. So instead of the inside microwave of the microwave oven, they gather, they harvest outside of the microwave oven. There are some leakage from the microwave oven. Of course, leakage power is very, very small. In this case, power level they receive is approximately 1 milliwatt only at a 5 centimeter distance. But with help of this 1 milliwatt, they create the 0.5 milliwatt power, and they drive the similar temperature systems. And this is an amazing figure. I suppose this is not computer graphic. University of Washington, famous professor, Josh Smith, their group develops a WIPS, wireless identification and sensor platform, and some group in University of Washington developed, it's a past experiment, augmented reality in contact rate. They said by support of the Google, they said on the website. And here you can see, I suppose these are antenna, and these are circuit rectifier. And with help of this ambient radio wave harvested radio wave, they create this ambient reality in contact rate, they said. But unfortunately, this project was stopped now. But we can get this information on the website. And after recently, this University of Washington group developed, for example, battery-free camera or battery-free sensor, etc. And additionally, I was very surprised to find it. So they developed battery-free cell phone. There is no battery in the cell phone. Of course, here you can see it's not a cell phone itself, not a smartphone, but only with this about 3 microwatt, they could transmit some very simple data as a telegram or etc. But this is a very excellent battery-free cell phone. Energy harvester, one of the good application of the energy harvester. And this is the other amazing news from China. So this is the news from the Huawei, China, about 8 years ago. And at that time, Huawei showed us to develop the wireless charger from the cell tower power to charge the drone. Of course, as I mentioned, sometimes recent drone requires very high power. So I suppose we can charge micro drone or small drone only by energy harvesting. But at that time, Huawei proposed this wireless charger, energy harvester, to charge a drone from the cell tower. But unfortunately, there was no developed result on the website or on the journal paper. But I was very surprised, and I expected this development by Huawei. But unfortunately, I suppose there was no advance now. So from here, technology I'd like to introduce how to increase efficiency at low input power. here. If input power is very small, tiny, and input voltage is not enough to overcome the junction voltage of the diode, how do we increase the efficiency? This is a technology. This is the same data. So from this 100 microwatt area, we have to gather the radio waves. And this is a historical review of the RF-DC conversion efficiency at the various input power. So over 1 watt, in the first lecture today, I mentioned recently optimum input power for the usual rectifier is 1 watt or 100 milliwatt. So around the 1 watt input power at the William Brown's days, we have already reached over 80%, 90% at 2.45 GHz. But if we decrease the power from 1 watt to milliwatt, microwatt, of course, efficiency has already not good, and efficiency is very low efficiency only. But year by year, we have a technology, and this conversion efficiency increasing year by year. And recently, so this is the one summary published in the journal paper, and weak powered rectifier. For example, they choose 500 megahertz and 900 megahertz, and this is the input power. And so minus 10 dBm indicate the 100 milliwatt as the input microwatt power, and minus 20 is 10 microwatt, and 1 microwatt here. And the efficiency currently, so close to 50% around 100 microwatt, and this is a real data around 1 milliwatt input power, about 10% only. And this is the other trend of the energy harvester versus frequency. So of course, efficiency decreases when we increase the frequency, as I mentioned. So please go back to the block diagram of the rectifier. There are some elements in this rectifier. So we have some way to revise the elements. First of all, as I mentioned, the easiest way to increase the receiving power is to use large antenna. Of course, there is no doubt. If we put a very large size of the antenna, we can increase the input power, and if we have a normal rectangle only, we can increase the efficiency and we can increase the power. There is no doubt, but it's not convenient. So for users especially. And usually for energy harvester, we consider the IoT device with a very small size, etc. So it's not real, but it's very interesting approach. And if we cannot use the large antenna, next element is rectifier, of course. So we have to consider how to increase the efficiency at the usual diode. And additionally, I'd like to introduce today, expansion of the frequency was a type. Type involves the energy storage of the battery. Of course, if the energy at each type is very small, but if we have a battery or energy harvester, we can charge this harvested wave, and for example, once in 1 minute or once in 10 minutes, we can use this storage power and we can use it. But this is the last method to increase the received power. So first of all, I would like to introduce antenna again. So as I mentioned again and again, we need a super gain antenna like I argued or the other, but unfortunately, so a lot of antenna professor, my friend, told me we cannot do it, we cannot develop it. But only one exception we have. In Kyoto University, about 10 years ago, my PhD student proposed a very interesting idea to develop the super gain antenna. So this is a very small resonator antenna, like your smartphone. And but only one resonator we can use our antenna. But this resonator characteristics of the antenna is very bad, so gain is usually minus. But in his PhD thesis, he proposed the combination of the wave mode in the one resonator, mode 1, mode 2, mode 3, etc. And he proposed this combination of the mode inside the resonator. As a result, we can increase the aperture area, even if we put a very small resonator. So this is a computer simulation result, and we put a very small point resonator here. But here you can see this red area is effective aperture area of this small resonator, and we can expand the aperture area. But theoretically, we did it. But unfortunately, when we developed a resonator, our resonator have some thickness of the size itself, and theoretically we have to put the various mode in one point. So if we have a size of the resonator, this mode combination is not good, and we could not develop the real multimode resonator as a super gain antenna. If you are interested in, we've already published some paper in the WPT, and please check it. But this is only one exception, and unfortunately, there is no super gain. And additionally, if we have even if we have a super gain antenna, the other problem occurs: directivity. As you know, if we have a high gain antenna, like a parabolic antenna, etc., it means directivity becomes very narrow. Because, as I mentioned maybe the first day, power itself is the same from the transmitter. But when we add the antenna gain, so wireless communication researcher consider EIRP, equivalent transmitting power, because transmitter power 1 watt multiply antenna gain. But 1 watt transmitter power is a 1 watt. It means they gather the other power from the other area, and they focus mainly in front, gain direction only. So if we have a larger antenna and antenna gain becomes high, directivity becomes very narrow because we transmit only 1 watt only. So this directivity, please consider when we would like to develop the energy harvester. But if we have a large gain antenna, large size antenna, we have to face this directivity to the source itself. So it seems it's not convenient, because hopefully we would like to gather the all directional wave from everything. But if we have a high gain antenna, in this case, from the front wave, we can gather enough power. But when source is away from the front gain, unfortunately, gain becomes very small, and we cannot gather enough power. So it involves the pros and cons. High gain is very good because it's a very large aperture. But suddenly, it becomes a very narrow directivity antenna, and sometimes it's not suitable for the energy harvester. So we have to consider this pros and cons to develop the large antenna for the energy harvester. And next, of course, revise update of the receiver circuit is better. So this is an explanation of the theory of the low power rectification. So my French friend, check it, the Carnot limitation. And this is efficiency of the low power harvester, as named Carnot limitation. This is a content of this formula. And based on this Carroll limitation formula, we can propose how to increase the efficiency here from this equation. So increasing the junction resistance of the diode is better. So sometimes we choose a short barrier diode with a high junction resistance and a high Q matching circuit to increase this junction voltage. And increase the non-linearity. So I will introduce the next. Instead of the short barrier diode, sometimes for low power only, tunnel diode, spin diode better sometimes. And low temperature, it's a general way to increase the efficiency, etc. And increase the input power. So of course, as I mentioned, the high gain antenna is better. And this is an important point. New circuit to add the high voltage. And of course, thermal energy, etc. we can use. So this diode is one of the very key technology for the energy harvester. And if we don't have a good diode for energy harvester, of course, we have to consider to develop the new circuit as an engineer. And this is a trend, historical trend for the energy harvester mainly, with a very interesting diodes. Of course, as I mentioned, we usually use short barrier diode for the usual rectifier, and efficiency becomes very high. But recently, after 60s or 70s, some interesting papers were published. Rectifier with tunnel diode, MIM diode, spin diodes. So maybe some of you know tunnel diode. The other name is Esaki diode. Esaki is a Nobel Prize winner of Japanese, and this has a negative resistance. Depends on the voltage. But so this is one example of the rectifier with tunnel diode. So, for example, at the high power efficiency of Schottky barrier diode becomes high. But if we choose a tunnel diode, around here efficiency becomes higher than the rectifier with the Schottky barrier diode. And of course, it depends on the diode parameter. And around here, efficiency suddenly decreases because around here, this diode, tunnel diode, becomes negative resistance. I suppose so. But around here, compared to the Schottky barrier diode, this rectifier with a tunnel diode is better, and we can expect this tunnel diode, the other diodes, for the energy harvester in near future. So I have not tried to develop the rectifier with a tunnel diode into the university, but in the world, for example, this is the other group in the world, and some group developing tunnel diode or rectifier just for the energy harvester. And next, circuit technology, because we are the engineer. If we have a limitation of the diode, we have a good circuit technology. So I'd like to introduce some interesting circuit suitable for energy harvester. So this is a typical energy harvester. Charge pump or wall clock Walton high voltage circuit. Maybe some of you will know this circuit. So this circuit is very good circuit to increase the output voltage, because input power is very small, but the user requests, for example, 5 volt or 3.3 volt or more. In this case, we have to increase the output voltage from the weak input micro power. So this series diode and the capacitance, this is a better understanding circuit, and we sum the rectified electricity step by step, and at last we reach the enough power to drive some small IoT sensor or etc. So if you check some paper about the energy harvester, some of them adopt this charge point or clock Gordon circuit. But as I mentioned in the first talk today, diode involves a loss factor. So in this case, this charge pump involves 10 loss factors. So from the viewpoint of the efficiency, it's not good. Of course, we can create enough voltage to drive the sensor from the weak power, but conversion efficiency is very poor, I think so. So, as an engineer, we have to consider the other way to increase the efficiency or voltage for the energy harvester. So, again, I explain how to increase the efficiency of the normal rectenna. So I explain a lot of way, but the most important point here, at the high voltage, even if input power is very weak. So this high voltage additive circuit is most important for energy harvester. So I checked a lot of papers, and I found a lot of interesting approach to increase the efficiency and to increase the output voltage for the energy harvester. So self-bias voltage, impedance matching at low input, and high impedance circuit and antenna, and reuse reflected microwave, differential rectenna and resonator adding circuit, selective matching circuit, etc. So I'd like to introduce in order. So this is the same circuit of the classic rectifier, but they use self-bias and self-synchronized rectifier. And so from some way, and they use the feedback to the rectified direct current, and as a here of the as a result, self-bias voltage up to the rectifier, and as a result, we can overcome the junction voltage and at last efficiency increase. Usually, for the detector, for example, detector is a very similar circuit of the rectifier, but it is usually use a wireless communication circuit. And for the detector, for the wireless communication system, input power is very weak, so they add the extra voltage at the diode to overcome the junction voltage. But as I mentioned sometime in my course, if we have a battery at the user, of course we can do it. We can add the bias voltage at the diode and we can overcome the junction voltage. But for the battery-free IoT sensor, etc., there is no battery outside. So this self-bias technology is very interesting, like our DC-DC converter. So this is a very interesting approach to the microwave detector. And the other group is impedance matching technology, and especially this MIT group proposed active impedance matching circuit. So in my previous talk, I introduced the Smith chart of the rectifier, and I told you only impedance matching point is only one point in the various frequency, various input power, and various connected load. So they installed this active impedance matching circuit here is a DC-DC, RF-DC conversion efficiency versus input power, and this due to this impedance matching circuit, they can increase the efficiency around the low power input area. So this is a very interesting approach by the input impedance matching at the low input power. And we Kyoto University, we focus on the output filter side. And we change the output filter area, and we propose some circuit. And as a result, for example, this 64 here, and we can increase the low power RF-DC conversion efficiency at the low power in this case. Approach is similar. They match the impedance at the input power side. And we, Kyoto University, input we, Kyoto University, match the impedance at the output side. It's the same. And the result, for example, we developed this energy harvester with optimization of the output filter. And at that time, with 1 milliwatt input power, we reached 100% efficiency at that time. And the other Japanese group develops Rectenna with reflected wave reuse. And they put diode here, and they change this line length. And from the user side, some reflection occurs. As I mentioned in the previous talk, Rectenna involves some reflection. And they reuse this reflected microwave again to the diode. And theoretically, we can use maximum double power, normal input power and reflected power to increase the RFDC convergence. But this is only one example from the Japanese university. And we, Kyoto University, developed the other way to reuse the reflected wave. We developed some kind of the reuse circuit. For example, this is the same circuit, but we add the circulator directly. And we use a rectifier, and through the circulator, we reuse the reflected wave, and again, this reflected wave to increase the efficiency, for example. But in this power combiner, this is it contains a big problem, because theoretically, power combiner or power splitter, we have to know the power level, power difference of the two input or two output. So in this case, this reflected wave, amplitude of the reflected wave changed by this input power, changed by the user side. So in this case, we cannot match the circuit impedance in this power combiner, input 1 and input 2. So, and in this case, reflected wave is very weak compared to the input wave. So it's not good. It's not the best because not good power combiner for the high power input and the low power reflected wave. So we change mind to use the reflected wave only. Again, here merge some reflected wave, and we combine the reflected wave, and again we revise it, we demerge it. It's very similar. And at last, we use the reflected wave to drive the other rectifier. So one bachelor student developed it, but they are not good rectifier, so there is no paper published to the world. And this is a very old matter, but this is a very interesting approach. So difference rectenna, we named it. So here we put the diode. And here you can see a microstrip antenna or slotted antenna. And usually output port of the antenna is only one. But in this case, very old Japanese professor in 1990 create two output ports here. And this slot antenna or the microstrip antenna, when we create two ports, and here we receive, for example, 0 degree microwave here, and from the opposite side, we got 180 degree difference output microwave here. And 0 degree and 180 degree microwave merged into the one diode. So as a result, this circuit is close to the voltage double. So usually we add only one signal, but we add the 150 degree difference signal at this diode, and as a result we add double voltage here. So this is named differential rectenna. And this is a very old rectifier. And they use the antenna itself as a differential operation. And the other Japanese professor proposed the 3 years later, and they propose a ratless circuit to create 0 and 180-degree difference, and they add again here, and this is the same differential operation. And recently, the other Japanese old Japanese professor developed two antenna with 2 antenna differential rectifier. So at that time, this Japanese professor developed one antenna for differential operation, but he developed two antenna for differential operation. So operation is the same as in these 3 rectangles. So in these differential rectangle, we can increase voltage about a double in this case. So this is a very interesting approach for the local rectangle. And directly to increase the voltage at the diode, some group at the resonator itself. For example, their group at the quarter-length short stub resonator here. And so, as you know, if we are the resonator, impedance becomes 0 or infinity, and hopefully we can increase the impedance around here by the resonator, and we can increase the voltage. So, in this case, minus 20 dBm, about 10 microwatt input at the UHF frequency, they reach over 40% efficiency. And this is a quarter-length short stub resonator, but the other Japanese professor developed directly put the LC resonator or the PLF resonator here. And as a result, slightly efficiency increased, they said. So, but here you can see, compared to the size of the rectifier, the electric resonator seems to be big. So we need to make it small. So, but this resonator rectangle is one interesting approach. And the other group proposed power dividing selective matching circuit to revise this low power area. So it's very close to the duality amplifier circuit. And they put 2 rectifier, high input and low input, and they change the matching circuit. And when high input is passing through the circuit, and high power is lead to this high power circuit. And when power becomes lower, impedance seems to be changed, and this low power is leads to this low power rectifier. So as a result, low power input and the high power input, both efficiency is very high. So this is a very interesting selectively matching rectifier. And this is the most famous and the most effective rectifier for energy harvesting, high impedance. As I mentioned now, when we use resonator, resonator has an impedance of the infinity, and as a result we can increase the voltage at the diode. So impedance itself will be higher, for example, a few kilowatts. As a result, we can increase the adding voltage to the diode, and as a result, we can increase the efficiency. It's a theory. And sometimes you already check the general paper of the energy harvester, their measurement data is measured with a few kilo user load. It's the same theory. If we add a very high load in user, we can increase the adding voltage at the diode, and we can increase the efficiency. But as I mentioned in the previous talk, we cannot choose a user. User requests us. So in the paper, it's easy to measure the RF conversion efficiency with a few kilo low, but sometimes user load is a few hundred ohm only, a few dozen ohm only. So in this case, antenna impedance and the circuit impedance itself, we choose a very high impedance, and we would like to increase the input added power at the diode. So this is a theoretical prediction by the same Professor Noguchi of the Kansai Institute of Technology, and they change the antenna resistance and the circuit impedance, and as a result, when they increase the antenna resistance or the antenna impedance, efficiency becomes higher, close to 100%. So it means when we increase the antenna impedance, we can increase the adding voltage at the diode, and as a result, efficiency become close to 100%. So, but in this case, over kilo ohm or more we need. So in this antenna is very strange shape, and high impedance antenna, it's very difficult to develop. So their group, Kansai Institute of Technology group, has a very good technology to develop a high impedance antenna and a high impedance circuit. And this is other analysis with a high impedance by Professor Noguchi, and high impedance creates a high voltage and a high efficiency. So these I introduce all approach to increase efficiency at the low input in my understanding. And additionally, of course, we have the other way, not on antenna, not on rectifying circuit, and if possible, we can change the waveform or the wave bandwidth to increase the efficiency. So, and usually, ambient radio wave is modulated, and the bandwidth for the energy harvester or for wireless communication is very wide. But rectifier, we usually design for the continuous wave, a very pure signal only. So next, we should develop wideband rectifier to gather the frequency area. So, for example, from the viewpoint of the antenna gain and bandwidth, Professor Noguchi explained us. So we have a relationship between the antenna gain and bandwidth, and to develop the wideband antenna, it's very difficult to keep the high gain and the bandwidth, as I said. And of course, wideband itself is very difficult, but there are some trial, and sometimes I read the recent journal paper of the dual band or triple band rectifier. But historically, for example, about 20 years ago, dual band rectifier has already developed by the Texas A&M Kaizen group. And this is one example of the triple band rectifier. And so sometimes, we would like to gather some ambient wave, TV, Wi-Fi, mobile, etc. Of course, it's a very good way to increase the efficiency from the ambient radio wave. And this is a very good broadband antenna for energy harvester developed by the Zoya Popovich group, Colorado University. And about 20 years ago, this paper, they have already developed a 2 to 18 gigahertz range antenna and rectifier. So this is a very excellent wideband rectifier, and efficiency is very good. And they keep development, and recently, so 5 years ago, they introduced this interesting energy harvester of T-shirts. So this is a wideband rectifier, and they print antenna and additionally diode here on our clothes, T-shirts. And so they measure this characteristic of the rectifier, and it's very interesting approach to expand the frequency range for the rectifier. And as the other group, for example, University of Liverpool, UK, has already developed this rectifier, and they combine broadband and high impedance rectifier here. So this is a very interesting rectifier. But their approach are mainly antenna side. If we can develop the broadband antenna, it's better for other Rectenna, they say. But please go back to the Rectenna. Rectenna involve antenna and circuit. So, and as I mentioned in the previous talk, we need a wideband matching, impedance matching point, even in circuit. So, the other group, Spanish group, proposed the broadband impedance matching circuit at the rectifier. So this is based on the broadband filter technology, broadband bandpass filter technology. But here you can see they can expand the frequency range from the 400 to about 1 gigahertz here. And this is a matching network for the broadband frequencies. And we, Kyoto University, developed a broadband matching circuit at the output filter. We like it to develop the output filter. And it's very simple sector type class F load, and as a result of this broadband matching circuit, we can expand the bandwidth of the rectifier, for example. And if possible, unfortunately we cannot control the waveform of the ambient radio wave, but for the wide beam WPT or the active WPT, if possible, we propose the pulse or multi-tone microwave applied to increase the efficiency. Because if we assume the same power is transmitted by continuous wave only or the pulse wave, here you can see if we use a pulse wave, suddenly microwave happen, and there is, we have no power time. It means as an average, if average is the same, so this period input power suddenly runs. So if we choose a pulse or multi-tone microwave, average power is the same, but input voltage some period becomes higher. So we carried out the experiment and the simulation, and we change the duty ratio. And when duty ratio is very small, average, and in this case average is the same, it means duty ratio is 0.1. Transmitting time only is 10 times higher power is input to the circuit. And the other 90% time, there is no power. But in this transmitting time only, 10 times higher microwave power is input. So as a result, duty ratio becomes small, efficiency becomes high. So this is one proposal. And the other group, for example, a Portuguese group, my friend, proposed a multi-tone microwave to increase rectifying, to increase our efficiency as a rectifier. So this is a very interesting approach. Instead of the broadcasting wave, or instead of the very pure sinusoidal wave, when we use a pulse or multi-tone, we can increase the power. But if average power is very high, this pulse wave becomes very much power, and in this case, unfortunately, this pulse input power overcome regular voltage. So in this case, it's not good effect for the rectifier. This is only a weak power case only. So this is our proposal and my friend's proposal. So that's all my talk. So thank you so much.
Thank you very much, Professor Naoki. Now the floor is open for query discussion.
So what is the main difference between WPT and energy harvesting?
Right. So as I mentioned, there is no exactly meaning there is no difference.
Power source.
But the power source is a big difference, and so waveform is a little bit different because it's enough to transmit a continuous wave only for wireless power transfer because we use a carrier only. We don't need a modulation for the active wireless power transfer. But for the energy harvester, we all radio wave applications are modulated because all about the radio wave communication are mainly for wireless communication. So modulated wave and continuous pure wave, it's very big difference between the active WPT and the energy harvester.
So we are modulating the wave in the energy harvesting.
Yeah, usually. And of course, so from the microwave over, there is no modulation because it's a heating wave. But if, for example, you would like to harvest a Wi-Fi, TV broadcasting wave, etc., all radio waves are modulated, so they have a very wide, wave broadcasting wave bandwidth. So, so for example, 25 years ago, we developed the energy harvester to harvest the 3G third generation mobile phone. At that time, we did it because at that time, modulated wave is very narrow, about 25 years ago. But recently, fourth generation or the fifth generation, so modulated wave is very wide, and now we cannot develop the enough energy harvester to gather the 5G or 4G radio wave because bandwidth becomes very wide.
So is this good to say about like if we are using microwave technology, so there is no need of modulation, so it means that is WPT.
Yeah,
if
so
we are using radio,
so I explain you, it's enough. But if we would like to develop the SWIFT, simultaneous information power and information technology, we should modulate the microwave. But it's enough to get to transmit the power by the continuous wave only. But we can modulate. So in this case, it's the same. There is no difference except the power density only.
Or in terms of energy harvesting, it means radio frequency we are modulating. So can we also modulate, if we modulate microwave technology, so it will be like energy harvesting?
Yeah.
Not in WPT.
Yeah.
So that is the main difference, like.
Yeah, I think so.
Thank you, sir.
Hello, sir. Sir, what type of diode type topology is better for rectification? Single diode or voltage multiplier?
Yeah. So usually for the normal rectifier, if we have a close to 1 watt input, Schottky barrier diode is the best currently. But today, now I explain. In future, for energy harvester or low power device, maybe tunnel diode or spin diode, etc. New diode is better. We've tried, for example, rectifier with a pin diode or normal diode, etc. Very long time ago. But pin diode we cannot use it. Or, for example, silicon carbide diode. Of course, any diode with a silicon carbide, FT or Fmax was not enough. So efficiency was very poor. So recently, Schottky barrier diode is better for the normal rectifier. And for energy harvester, now we choose a single Schottky barrier diode mainly, but in near future, tunnel diode or the other diode can be expected.
So single diode or voltage diode topology, which one?
It depends on the user. So we continuously usually use a single diode, single shunt diode mainly. But if you need more power, for example, it's a very rare case, I suppose. So, but for example, a user requests, for example, 10 watt 100 watt, we cannot develop one diode rectifier because so diode cannot rectify enough power. In this case, double diode or triple diode like charge pump, etc. We can use.
That will increase the efficiency, right?
Yeah. And of course, if we increase the number of diode, loss factor increases and it involves the cross and more. But about 20 years ago, we've already developed totally 16 diode rectifier, and we combine the power combiner, and totally 100 rectifier we've developed with 256 diodes. For example, it's very long historical development. Yeah, but we succeeded in rectifying 100 watt directly with a normal Schottky barrier diode, but we use 256 diode in one rectifier, for example.
Thanks.
Any other query? Okay. There is no query, then we conclude this morning half session of this for today. We'll meet again 2 o'clock for tutorial session.